Okay, everybody, see, we have another question, which is question number 5. It is based on Bohr's atom model as well as a little bit of mathematical manipulation. And we have the ideas of modern physics like de Broglie wavelength. So let's try and solve this problem. So we have the given data like consider a hydrogen atom with Vk, Rk, Kk represents the velocity, orbital radius and kinetic energy of the electron in the kth orbit. Then the electron undergoes a transition from nth orbit emitting radiation corresponding to a Lyman series. Considering h to be the Planck's constant and epsilon naught as permittivity of free space, which are the correct statements. So we need to check each and every option here and we'll go for it. Okay. So as you are all aware of this, suppose if we have some nucleus here, especially it is hydrogen atom, okay? So an electron will be revolving around at some radius, let's say. So here the given data is our electron is in some kth orbit and it is moving with a velocity vk and radius will be rk. That's given. Now as this is moving, it can transition from excited state to ground state. So they are saying if it is undergoing a Lyman transition. So you know that Lyman transition from any given energy level, if the transition happens to n equals 1, then we know that it belongs to Lyman series, correct? Now here we have an electron which is orbiting in nth orbit. Okay, from nth orbit it is just jumping to n equals 1. Now we need to just check out the options and see, like, comment on how things will happen with the kinetic energy and de Broglie wavelength and all. Let's have a look into the question. Yeah, so you can see here in the question we need to comment on magnitude of change in kinetic energy of the electron. For that we need an expression for kinetic energy. So let's see like how to get the kinetic energy expression. So we have kinetic energy of the particle which is in the nth orbit is given by half mass of the electron and velocity in the nth orbit squared, right? This is the basic expression for kinetic energy. Now we also know this, the angular momentum of a given electron in the orbit is given by mvr. So we have vn Rn because velocity corresponding to nth orbit, radius corresponding to nth orbit, which is equal to nh by 2 pi. And this we know from what? We know this from Bohr's postulate. We know this idea. So we have these two equations, right? After this, let's do a little bit of manipulation of this and rewrite this one in a different way. So I'll just make some space here. So we have kinetic energy expression and angular momentum in the nth orbit, this expression, okay? So kinetic energy will take the expression half m vn and we'll be writing another v, right? Velocity in the nth orbit. By using this expression, we'll rewrite it, okay? So we can write velocity in the nth orbit as nh by 2 pi divided by m times of rn, okay? So we'll have nh by 2 pi divided by m times of r, m times of r. This is what we'll get. This is the expression we have for kinetic energy. Let's simplify this. The kinetic energy we will get in the nth orbit as 1 over 4 or nh by 4 pi. nh by 4 pi times we'll have vn by r. vn by r. So with this expression, we know that kinetic energy will be same as total energy with a negative sign. We also know this, right? So kinetic energy and total energy will be related like this because we are dealing with central forces and these ideas. We have learned this, right? So this is the expression for kinetic energy, this is the expression for total energy. With this, we will first verify our change in kinetic energy. I'll erase this part. So changes happening to our kinetic energy. So delta K, meaning kinetic energy in the first orbit minus kinetic energy in the nth orbit, because it is transiting from nth orbit to first orbit, right? So we have kinetic energy in the first orbit, right? So we'll take this expression, put n equals 1 and v1 r1, right? So h by 4 pi, and v1 by r1 minus kinetic energy in the nth orbit, exact same relation, we just substitute here. So nh vn by 4 pi times of rn. Just take the common factors, so h by 4 pi outside, so we'll have v1 by r1 minus nvn by rn. So that's our change in kinetic energy. So let's look at the options. So you'll see that the kinetic energy change in the first option as h by 4 pi, nvn by rn minus of v1 by r1. Anyways, they are asking magnitude, right? So minus sign, it doesn't matter. So we can just say that magnitude wise, this option is correct. So we can write this is option A, meaning you can write h by 4 pi magnitude wise, because or else we have to write negative. So nvn by rn minus of v1 by r1. So that's the change in kinetic energy. So option A would be right answer. Okay. Now using this logic, we can think of total energy change. So total energy change, if you observe, don't you think from this expression, the total energy change should be exact same value with a negative sign? So again, we'll go back to our options. You can see that change in total energy, the fourth option, option D, we have h by 4 pi times nvn by n minus of v1 by r. This would be the changes happening to the total energy. So what we did, we took final energy of the first orbit, okay, and final, like initial energy in total energy in the nth orbit, and we took the ratio, difference of it. So this is nothing but final E1 minus of En. This is the final energy and this is the initial energy. We are taking the difference of it, and as we express this one, we will get this. So h by 4 pi nvn by rn, this would be rn, right? nvn by rn minus of v1 by r1. So this is the change in total energy we are having. But in the options, if you see, in the options they are giving h by, in the options if you see, it will be h by 2 pi times v1 by r1 minus of nvn by rn, it seems. Meaning they are expressing in magnitude wise, we can reverse this, that is not a problem. But we wanted 4 pi, but in the option it is saying 2 pi, right? Which is not correct. So option D, right, that would be incorrect. Option D would be incorrect. Option A is correct, option D is incorrect. So we are done with two parts of the question. Now let's go with other ideas also. So let's take up the question again. So you'll see that we need to think about now magnitude of change in de Broglie wavelength as well as frequency of radiation emitted in our given situation, right? So I will erase all these things. And we'll think about now de Broglie wavelength. See, de Broglie wavelength is given as h by momentum in the denominator, but here we have velocity of a particle which is moving in the nth orbit, right? So we have h by mvn. So we have already developed kinetic energy in the nth orbit. Kinetic energy in the nth orbit is given as nh by 4 pi times vn by rn. This is the expression that we have already developed. This we did in the last section, right? So this expression we have, and velocity of the nth orbit, right? Let us reorganize this in the other way. So we can just write 4 pi Kn Rn divided by Nh. We are just reorganizing it. Then I'm sure that we all would have memorized this. The radius of electron, when it is in some nth orbit, it is epsilon naught n squared h squared pi m ze squared. So here z equals 1, right? So we have the expression for radius of the electron moving in an nth orbit in hydrogen atom given by this epsilon naught n squared h squared by pi m z squared. Let's plug this information here and write the value of Vn. Okay, so as we write this one, we'll get 4 pi Kn by Nh, right? And Rn is given epsilon naught n squared h squared by pi m e squared. Let's simplify this. Let me give some space here. That's Rn. Now n and h gone, so we'll have the pi value also gone. So we'll have 4 Kn epsilon naught Nh, 4 Kn epsilon naught Nh by m e squared. That's velocity in the nth orbit. Okay, so velocity in the nth orbit we got. Now let's reorganize this a bit. I'll just transfer this m here. So that's our momentum, right? So momentum is 4 Kn epsilon naught Nh by e squared. So we'll plug this information here and write lambda equals, I'm just substituting, nothing much. So mvn would be 4 Kn epsilon naught Nh and e squared here. Okay, so we finally got lambda n de Broglie wavelength in the nth orbit. If de Broglie wavelength in nth orbit is this value, right, then we can just get rid of this h dependency, and lambda in first orbit would be e squared by 4 epsilon naught. Let me write this n, it is Kn and n. If it is first orbit, it would be e squared by 4 epsilon naught K1, right? So changes in the de Broglie wavelength, lambda 1 minus lambda n. This is a final state, this is the initial state. When you take difference of it, you will have e squared by 4 epsilon naught, right? That's the common thing. And you will have, this is the final one, so it is 1 by K1 minus 1 by nkn. This is what we have. But if you look at the options, they have given the changes happening to the de Broglie wavelength as shown, that e squared by 4 epsilon naught, that's what we have, and 1 by Kn minus of 1 by K1, it seems, right? But they are using magnitude, yeah? So they are using magnitude. You can observe that even if I use magnitude here, even if I use magnitude and revert these two, but still n will be missing, right? Since n is missing, we can surely say that option B, right? That because we are checking de Broglie wavelength, that option B, right? That would be wrong. Option B would be wrong option. Okay. Now going further, we'll have to check option C then. So option C, I'll erase a little bit here and make some space and we'll solve it. So I'll erase this part a bit. We know that it is transferred from higher energy nth state to lower energy 1. So we'll have, that is h nu, and energy in the nth orbit, I think we would have memorized this. Energy in the nth orbit. Energy in the nth orbit would be in general ZE squared by 8 pi epsilon naught r, right? In n, because it's just like what, half of the potential energy. So this we know, and negative because the total energy bound state. So I think you would have memorized this. Then we'll just use the difference of this. So h nu would be, say z equals 1 here in this case. So we'll have final energy this minus of that, right? So e squared minus 8 pi epsilon naught Rn minus plus e squared by 8 pi epsilon naught R1. That's the change, right? So we'll have nu equals, we'll take all the terms common, which are present in both the terms. So E squared by 8 pi epsilon naught 1 by R1 minus 1 by Rn, right? And here we'll have h nu. I'll be transferring that h here. So let's check out the options now. So do we have E squared by 8 pi epsilon naught h into 1 by R1 minus 1 by R1 minus 1 by Rn? Check. In option C, if you observe, we have frequency of radiation emitted can be expressed as E squared by 8 pi epsilon naught h 1 by R1 minus 1 by Rn. So absolutely right. So in this question we got option A and option C are correct. Option B and option D are incorrect. So I hope this problem is pretty simple. It had Bohr's atom model idea, and you should know the basic postulates. That is one more thing. Then you should also know the mathematical manipulation. You have to check out the options and see like what best we can do to express in a given terms.
Okay. Question number 6, paper 1. It says a particle is thrown with a speed v from a point O at an angle theta with the horizontal plane such that it passes through some point P which is at a height of 1 meter at a horizontal distance of 5 meter from O. So 5, 1, acceleration g downward, and you have to pick the correct options out of the following. So I'll just start with x, y equations. So initial velocity, and for y, gt square, and write tan theta as y plus half gt square by x. So that gives me gt square is 2 times x tan theta minus y, and v I can write as x by cos theta into t, and the y component of speed at any later instant is u sin theta minus gt, right? So u sin theta minus gt in terms of x can write as x tan theta by t minus gt, or x tan theta minus gt square by t. So I'm just going to use this to check the sign of Vy. If it's negative, then you know it's after reaching maximum height. If it is positive, this is before reaching maximum height. So for the different cases given, theta equal to 45. If you put theta equal to 45, you'll get 5 minus 1, 4. So gt square is 8, or t square is 8 by g, or t is 2 times root of 2 by g. Substitute that here, 5 cos 45, 1 by root 2, and then this is 2 root 2 root g. So 5 by 2 root of g. That's option A. Option A is correct. And now to check whether it reaches the point after it reaches the maximum height, just check the y component of velocity. X tan theta is 5, gt square is 8. 5 minus 8 will be, so for theta equal to 45, case Vy will be 5 minus 8 by t. I only need to check the sign. This is less than 0, means it's going down, so maximum height has already been reached. So option A and option B are correct. To check for the C and D options, if you put theta equal to 30 degrees in this, you'll get gt square is 2 times 5 by root 3 minus 1. Repeat here, you'll get 5 by root 3 minus 10 by root 3 minus 2 by t. It is 2 minus 5 by 5 5 by root 3 by t. Again, just looking for the sign. 5 by root 3 approximately 1.7. This will be more than 2. So Vy will again be negative. That means here also the maximum height has already been reached. The particle is going downward. So option C is not correct. And option D, if you put tan theta equal to 1 by 5, you'll get t equal to 0, which is not an acceptable solution. So A and B are the only correct options for this.
Paper 1, question number 7, physics. A quasi-static cycle of monoatomic ideal gas contains an isothermal process. So first of all, they're telling us the gas is monoatomic. We know degrees of freedom will be 3. Degrees of freedom will be 3. It's monoatomic. Gas contains an isothermal process AB. They have given the graph. I'll copy the graph at first. So y-axis, there is pressure. X-axis, there is volume. The process is drawn something like this. So this point they are calling as A, this point as B, this point as C. A to B, B to C, C to A is the process direction. At A, they have shown the volume is V1. At B and C together, it's a vertical line, so the volume is V2. Y-axis pressure, x-axis volume. A quasi-static cycle of monoatomic ideal gas contains an isothermal process AB. So at AB, the temperatures will be constant. Did they give how much temperatures? Okay. Followed by an isochoric process BC and an adiabatic process CA as shown in the figure. The volumes of the gas are V1 and V2 at A and B respectively. If the cycle has heat input Q in and output Q out, then the efficiency of the cycle is defined as eta equals Q in minus Q out. That's basically the net work done in the cyclic process, right? Because delta U will be 0. Q net equals W net. The correct statements is or are given. Ln 2 is 0.7. They have given ln 2 value as well. Okay. So let's check the options. Option A, if V2 by V1 is 8, the heat released in the process BC is smaller than the heat absorbed in the process AB. B says for given value of V2 by V1. So every option they are dealing with V2 by V1. Seems okay. For given value of V2 by V1, eta does not depend on temperature of isothermal process. It has efficiency. Okay. And then option C, then temperature of the gas at A is 4 times the temperature of gas at C. And D, they are comparing pressures. So we have to get pressure comparison, temperature comparison, and we have to get eta value and then compare Q values. Okay. So first of all, let's assume temperature. They didn't give anything. We'll assume temperature at A as T1. Process AB is isothermal. So temperature at B will also be T1. Then B to C is isochoric. They are saying the volume will be constant, but the pressure will be changing. Let me call pressure at A as P1, pressure at B as P2, and pressure at C as P3, right? And then at C, the temperature, well, temperatures could also change because it's isochoric, not isothermal anymore. So this is T2, but T2 to T1, C to A will be an adiabatic process. So first, they have given V2 by V1 is 8. The heat released in the process BC, it's smaller than the heat absorbed in the process AB. How do we compare the heats? Okay, so I could say for this complete cyclic process, delta U will be 0 for cyclic process. Starting point, ending point of the process will be same. So delta U will be equal to 0. That means Q minus W will be 0. Means Q for the cycle will be equal to W for the cycle. Q for complete cyclic process will be work done for complete cyclic process as well. Now work done for complete cyclic process, it appears that the cycle is clockwise. So for clockwise cycle, the work done by gas will be positive. That means heat is supplied to the gas effectively. Q cycle will also be positive. Heat is effectively supplied to the gas. Now, in the 3 steps, what is really happening with heat? A to B, isothermal process, but volume is increasing. Delta U is 0, but work is positive. So Q is positive. QAB is greater than 0. We know that. And then QBC, from B to C, isochoric process. Pressures are decreasing. Temperatures will be decreasing. So delta U is negative, work done is 0. Delta U is negative, work done is 0. Q will be negative. So QBC is negative, right? So in AB, heat is supplied to gas, BC heat is taken out, and CA is anyways adiabatic, so nothing. So overall, net heat supplied to the gas is heat supplied in AB minus the heat amount removed in BC. And that's what is supposed to be W cycle, but we know work done for complete cyclic process is positive. So can I say heat supplied will be more than heat removed, only then the net heat will be supplied to the gas? Option A is asking us to compare the heat released in process BC, and they are saying it's less than the heat absorbed in process AB. Makes sense? Heat supplied to the gas is more than the heat removed. So option A is correct. I'll write it here. A is correct. Then for a given value of V2 by V1, eta does not depend on the temperature of isothermal process. We have to get eta expression, and then we have to compare pressures and temperature. I think going with comparison of pressure and temperature could be easy things. First things first, right? Easy things first. Let's go with pressure, temperature, volume comparisons. So let's check pressures. What will be relations? They are asking us to compare the pressures between A and B. The process A to B is isothermal. For isothermal process, we know pressure into volume is constant. So I could say P1 V1 equals P2 V2. P1 V1 equals P2 V2. P1 V1 equals P2 V2. Fine. Isothermal process. So we can compare the pressures easily, right? They are asking pressure at A. So they want us to get relation between P1 by P2, pressure at A by pressure at B. That's what they are asking. It's 4 times. Let's verify. P1 by P2 from here will be V2 divided by V1. And what is the V2 by V1 ratio they have given? For option D, V2 by V1 is 8. V2 by V1 is 8. So this thing is 8. So P1 by P2 will be 8. 8 times. So option D is not correct because it's saying the pressure P1 by P2 is 4 times, but actually we are getting 8 times. So D will not be correct. Then let's check the temperature. Option C, temperature relations between points A and C. How do we compare temperatures between points A and C? So between A and C, the process is adiabatic. So maybe we can write adiabatic process relation. For adiabatic process, PV to the power gamma is constant or TV power gamma minus 1 is constant. They have given volume ratio. So let's use TV power gamma minus 1. TV power gamma minus 1 is constant. This we are talking about process CA, right? So I could say T1 V1 to the power gamma minus 1. Monoatomic gas, gamma is 5 by 3. Gamma minus 1 is 2 by 3. 2 by 3 equals T2 V2 to the power 2 by 3. So we get T1 and T2. They are asking us to compare temperature at A by temperature of C. So I'll write temperature at A. T1 by T2 is what they are asking. T1 by T2 is V2 by V1 to the power 2 by 3. They have given V2 by V1 as 8. 8 to the power 2 by 3. 8 square is 64. Cube root is 4. So this is basically 4, right? T1 by T2 is 4. Temperature at A is 4 times the temperature of C. Yes, that's correct. Option C is correct. A is correct, C is correct, D is definitely wrong. The one that we have to yet check is D. For a given value, they are asking now efficiency. Now that's the usually lengthier part because we can find the relations at first and then maybe we can use that for finding efficiency. So efficiency, what is the expression in general? They have given it already. We know it in this. So net work done by the gas in cyclic process, that's Q cycle. So Q in minus Q out. Q in minus Q out divided by Q in. So basically 1 minus heat lost divided by heat gained, right? Heat lost, in which state is the gas losing the heat? BC divided by heat gained by gas. In which process is the gas receiving heat? AB. QAB, that's it. But keep in mind, when we write this QBC, it has to be the amount of heat lost. When we calculate it using formula, the formula that we have are generally for heat gained by the gas, heat received by the gas. So better make sure that we are taking modulus of that quantity. So let's try to get expressions for QBC and QAB. First of all, QAB. AB is what kind of process? Isothermal. So how do we get heat for isothermal process? Delta U is 0. So W itself, isothermal process, right? Delta U is 0. So Q and W will be same. For isothermal process, work done was nRT ln V final by V initial. Q will also be same. N R, the temperature at which that process was working was T1 ln V final by V initial. V final is V2 divided by V1, right? For isothermal process, this will be expression for QAB. I think that's fine. So maybe we can substitute V2 by V1. Well, we'll got the expression. We'll compare the expressions later on. Also, let's try to get QBC. BC process is isochoric. Isochoric process, work done will be 0. So Q will be delta U. Delta U for isochoric is NCV delta T. So yeah, correct. Q will also be NCV delta T. But CV for ideal gas, monoatomic gas will be FR by 2, 3R by 2. So 3 by 2 NR. And then what shall be this delta T? Final temperature minus initial, T2 minus T1. T2 minus T1. So what do we get here? 3 by 2 NR. I think if we want to calculate this, better we get in terms of T1 rather than both, right? Can we convert T2 in terms of T1? We got some conversion, T2 in terms of T1. So T2 can be written as T1 into V1 by V2 power 2 by 3. T2 is T1 into V1 by V2 to the power 2 by 3 minus T1. So what do we get? We can take T1 out. 3 by 2 NR T1 times V1 by V2 times 2 by 3 minus 1. So what do we get? We got this expression for QBC, but we know they are talking about for given value of V2 by V1, eta does not depend. They are not asking us values. They're just asking whether it depends or not. Let's just get the expression. So eta equals 1 minus mod of QBC. Well, mod of QBC, we have to take modulus, but we know QBC, we calculated this as heat gained by gas, so heat lost. Basically, if this quantity is negative, to take modulus, we have to take negative of this. So take 1 minus, I'll write 3 by 2 NR T1 into 1 minus V1 by V2 power 2 by 3, all that divided by QAB. QAB is nRT1 ln V2 by V1. So we get nRT1 cancelled. Eta equals 1 minus 3 by 2, 1 minus V1 by V2 power 2 by 3, all that divided by ln of V2 by V1. For a given value of V2 by V1, eta does not depend on temperature of the isothermal process. Yeah, it doesn't depend on T1, right? Option B is also correct. They didn't ask value, we don't have to substitute anything. Just, does it depend or not? Yeah, A is correct, C is correct, A, B, C will be the answer. D is wrong. Paper 1, question number 8, physics. The question says, the electric field associated with an electromagnetic wave traveling in vacuum is given by E naught sine 3y plus 4z plus omega t I cap. So they have given electric field as E naught sine 3y plus 4z plus omega t I cap, where omega is the angular frequency. All quantities are in SI units. The correct statements about the wave is or are. So they have given the speed of light in vacuum as 3 into 10 power 8 meter per second. So option A, the wave is traveling in minus 1 by 5, 3j cap plus 4k cap direction. Now, how do we judge the direction in which the wave is traveling? We can compare this with standard equation. I could say, standard equation for electric field could be treated as E naught sine, 3 space. It could be omega t minus k vector dot r vector times n gap. N gap is the direction of electric field fluctuation, whereas r vector is the position vector of point at which the electric field power is calculated, or that light is traveling through that point position coordinates. K vector is the wave vector for that wave. Now, for this problem, electric field is fluctuating in I cap direction, x direction. So electric field fluctuates in a direction perpendicular to wave velocity, and k vector will be in the direction of wave velocity. So we could write k vector dot r cap as k vector dot r vector as k vector could be understood. Well, k vector could in general be kx I cap plus ky j cap plus kz k cap. But as we know, n cap, the electric field fluctuates in x direction, that was I cap. So velocity of wave will be perpendicular to x. So x component of velocity of wave will be 0. So for wave vector also, x component will be 0. So this quantity will be 0. K vector could then be understood as ky j cap plus kz k cap for this problem, as electric field direction is given. And then r vector for any point through which that light wave is passing can be given as x I cap plus y j cap plus z k cap, assuming the coordinates of the point are x comma y comma z. So what would be k vector dot r vector? We could write k vector dot r vector as, so x into 0, then there will be y ky plus z kz. That is k vector dot r vector. And comparing it with the original equation given, we can understand. So this given in the question 3y plus 4z is minus of k vector dot r vector. So that's minus of 3y plus 4z. Now comparing both these equations, we could say ky equals 3 and kz equals 4. We get y coordinate, z coordinate, ky and kz. So the wave is traveling in that direction. So in this case, we get 3y plus 4z as minus k vector dot r vector. So option A, the wave is traveling in minus 1 by 5, 3j cap plus 4k cap direction. Now we get y coordinate and z, y component and z component of k vector as 3 and 4. So 3i cap plus 3j cap plus 4k cap is fine. But as these coordinates are positive, the wave should be traveling in negative directions of that, right? So in this case, we get ky equals minus 3, kz equals minus 4. There was a minus sign in between. So option A, when we want to find the direction in which the wave is traveling, so k vector's direction alone, k vector for this problem appears to be minus 3i cap, minus 3j cap, minus 4k cap. If we want direction alone, so we have to get a unit vector in that direction divided by its magnitude. Option A appears to be correct. So magnitude of k vector is 5. Option A is correct. Then option B, the magnitude of the wave vector is 0.5. Magnitude of wave vector is in front of us, 3j cap, minus 3j cap, minus 4k cap. So the magnitude is 5. If k vector's magnitude is 5, magnitude of wave vector can't be 0.5. Option B is wrong. It should have been 5. B is not correct. Then option C, the value of omega. How do we get omega? We know for any wave, we get V, speed of the wave, equals omega divided by k. So omega can be calculated as V times k if you just want magnitudes and all. So speed of light in vacuum 3 into 10 power 8 multiplied by k. K value is given as in magnitudes, we just got it as 5. So we get 15 into 10 power 8. That is basically 1.5 into 10 power 9. So 1.5 into 10 power 9 radian per second. So that will be option C is also correct. The magnetic field associated with this wave is given by. Now, what things do we know about magnetic field? Its magnitude and direction. First of all, magnitude of magnetic field could be given something like this. Speed of light will be magnitude of electric field amplitude divided by magnetic field amplitude. So we get B naught equals E naught divided by C. That part is understandable. Then the phase of magnetic field fluctuation will be same as the phase of electric field fluctuation. So that 3y plus 4z plus omega t part is common as that of electric field. That part is also fine. Now the only thing we have to choose is direction for magnetic field. Well, magnetic field's direction, we can get it as E naught cap cross B naught cap should be the direction of k cap. So right hand thumb rule for directions of electric field, magnetic field and the wave propagation relations. So we get E naught cap cross B naught cap equals k cap. And if we check with this equation, E naught cap is E naught cap. So direction of E naught vector is along I cap. Then B naught cap, we can just write some Bx I cap plus By cap plus Bz cap, and we can compare that with k cap's direction of wave propagation. Wave propagation is direction of k vector. So that's minus 3j cap minus 4k cap divided by 5. Well, we can solve all that, but do we really need to? If we check the last part of the direction, it should have been a unit vector, that 4j cap minus 3k cap. So even if the direction cosines may appear to be in relation, in proportion, but still it's not a unit vector. 4j cap minus 3k cap, it's not a unit vector. So overall that affects the magnitude of magnetic field. So it won't be correct, right? Even if that was correct, the denominator should have been 5. Well, if we want to check, we could also go in details. So I could write cross product first. I cap, J cap, K cap, E naught cap. E naught electric field is only along x-axis. So electric field is only along x-axis. We could write E naught, then J cap 0, y component 0, z component 0 for electric field vector, right? So along x-axis, amplitude is E naught. We want to get unit vector only in that direction, right? We'll treat it as 1. And then B naught cap, magnetic field. We don't know the direction, but we know for sure it has to be perpendicular to electric field and it has to be perpendicular to K vector as well. But for now, I'll write Bx, By, and Bz, and such that we know this has to be in the direction of K cap. So direction of K cap is minus 3 J cap minus 4 K cap divided by 5. This will be K cap. So we have to evaluate this. And we understand root of Bx squared plus By squared plus Bz squared should be equal to 1. Besides, if electric field is only along x-axis, there cannot be magnetic field along x-axis. Both the fields should be perpendicular to each other. So Bx will anyways be equal to 0. Well, I'll substitute 0 here itself. So we can write, this will be I cap into 0 minus 0 nothing minus J cap into Bz minus 0. So minus Bz J cap and then plus K cap into By minus 0. So plus By K cap. That should be minus 3 J cap minus 4 K cap divided by 5. Besides, root of Bz square plus By square will be equal to 1. So we can tally both the sides. Turns out Bz will be 3 by 5 and By will be minus 4 by 5. So that doesn't appear to be matching with the option. First of all, that 5 is also missing in the solution. So we would get Bz as 3 by 5. For J cap, we are getting 3 by 5. Okay, so let us see again. Bz is 3 by 5. We're getting it right. J cap Bz 0. So that's fine. Minus Bz into J cap and K cap into By. So we are getting By as minus 4 by 5. E naught cap cross B naught cap is K cap. So Bz, By. So this doesn't appear to be matching with option D. So the answer here will be A is correct, C is correct, B and D will be wrong.